Thanks. Apologies for that. Yes, I would just like to welcome everyone to week 2 and all the best. My name is Arwani. I'm joining from NITheP, Cape Town. Thank you.
Thank you very much. I'm glad we could see you because I think many people have worked with you guys and they haven't met you before. So thank you so much for that. Thank you. Thanks for all the hard work. Benjamin, before we go to Tutukile, do you want to quickly come on camera and just say something? I saw your message here. All the best. Oh, mic not working. Okay, that's fine. Okay, Benjamin, then from my side, huge thanks to you and your whole team for everything last week. Let's see if we can quickly get hold of Tutukile to say hi. Tutukile, are you here? Okay, at some other time, I'm going to ask Tutukile to say hi to everyone. I know she's traveling somewhere and I know she's busy walking somewhere, so that's fine. What I wanted to say is thank you very much for being here today. Please make the best of this week. Please give us feedback. And also, if you haven't joined our mailing list, please do so, because then you'll be reaching then you'll be receiving amazing alerts such as this course and many others. So thank you very much for everybody making this possible. And yeah, let's make the best of it. Thank you. I'm handing over now to Dr. Graham Pleasance soon so that he can start with his lecture for today. Thank you.
Yeah, just.
Okay. Waiting.
I just want to check that everybody can hear me.
On the...
Fine. Okay, good.
Guys, I'm going to give them the Zoom link. You can just start because the others are all waiting. So I think, don't worry about this now. I'll share the Zoom link. Hello, how are you? Good, thank you. Yeah, hold on a second. I've heard hold on a second. For the same price. Okay, wonderful. Yeah, now you share with me.
Okay, hopefully everybody can see my screen. Let me just turn my camera on if possible.
Forward page, so like this. One person and then we just email it to everybody. Everybody's email address easier. Okay.
Can I get something from the chat just to make sure that you can see me, you can hear me? Okay, I'm presuming that everything's fine then. Okay, yeah, so yeah, sorry for the slight delay at our end. I just want to say good morning, everyone, and welcome to the second week in the NITheC CHPC summer school. So let me just start by saying that unfortunately, so Professor Francesco Priticcioni, who was meant to deliver these lectures, unfortunately he couldn't be here today. So I'm filling in for him. So today's lectures are essentially on a kind of an introduction to what we call computational thinking. So this is kind of a way, it's a way of thinking that influences in how we go about problem solving, but also in the context of computing, how we kind of design and implement algorithms. So obviously I'll talk a little bit more about this during today's lecture. Okay. So this is, yeah, so a kind of very generic outline. So I'll try to define what we actually mean by computational thinking, and then I'll go on to formalize the kind of the core principles behind this way, behind the ways of computational thinking. And then towards the end of this lecture, what I'll do is I'll give you an example algorithm, so a way of computing pi from what's called the Leibniz formula. And then I'll also give you an opportunity to write your own code for computing a Fibonacci sequence. Okay, so let's start with the following. So maybe go into some historical context behind what we mean by computational thinking. So as I said, like, this lecture introduces the fundamental ideas of computational thinking, and tries to kind of justify why why we're interested in these ideas behind computational thinking. So the goal is to demonstrate how computational thinking just goes beyond programming, so just writing code. So it's kind of a way of adopting also a kind of problem-solving mindset, which obviously is important in the context of science, so and in maths and engineering, etc. Okay, so as I mentioned, there's kind of these core principles behind what we call computational thinking. So we can kind of categorize these in kind of roughly 4 ways. So these are decomposition, pattern recognition, abstraction, and algorithmic design. And what I'll do is I'll go into these kind of principles, kind of elucidate them a bit more, and then in a kind of very basic way introduce you to some basic kind of practical examples of how we can apply these principles in writing code. And then, as I said, we can go a bit later into kind of short exercise where you can try to apply this yourself. Okay. So talking about the history, I won't be able to pronounce this person's name correctly, but so I think it's pronounced Al-Khwarizmi. So it was a kind of 9th century philosopher, polymath, mathematician. And so the term algorithm is derived from his name. And so he was, if you want to attribute a starting point to ways of computational thinking, I'm assuming you could probably start with this person. So he kind of formalized, in a sense, the ideas of breaking down a problem into steps, which can be repeated. So essentially an algorithm. He also made quite important contributions to things like algebra. And a little bit more recently, so we had someone like Alan Turing. So he showed that or at least one of his many achievements, he showed that any computable task can be executed by a simple device with a well-defined set of rules. So this is known as a kind of universal Turing machine. And so he kind of, with this kind of model of computation, like laid the groundwork of modern computational science, which was obviously strongly influenced by the ideas behind computational thinking. So also more recently, so Donald Knuth has I think it's a book, so The Art of Computer Programming. And so in this, he emphasized like rigorous analysis of algorithms, and kind of building on previous work, pushed the importance of kind of logical problem solving. And another person to perhaps highlight is Jeanette Wing. So she popularized the term computational thinking. So obviously the title of this lecture, and kind of advocating the fact that it's not just a skill for kind of programmers and computer scientists, but it's a universally applicable skill. So a type of skill which is kind of crucial in the context of problem solving, and things of that nature. Okay, and so as I kind of already mentioned, why is computational thinking important? Why is the history behind it important? Because whether you're a physicist, whether you're a biologist, whether you're a data scientist, most real world problems involve trying to take something which is incredibly complex and trying to then break it down into smaller components, which are much more easily analyzable, and then trying to come up with a way of kind of solving each of these problems. So, once you've broken down the problem, solving each of these kind of smaller problems, which then help you kind of unlock the bigger picture. And so, yeah, so this is applicable in the context of things like software simulations, systematic manual methods, etc. Okay, so I previously mentioned these kind of these four kind of core principles behind computational thinking. So these, just to reiterate again, so these were decomposition, pattern recognition, abstraction, and algorithmic design. So let's just kind of go through them one by one to kind of elucidate a little bit more thoroughly what we mean by each of these four things. So so decomposition is where we start with some kind of problem that we want to solve. And what decomposition does is we kind of take that problem and start by kind of splitting it into kind of smaller, more manageable parts. So I think the example that's given on this slide is kind of building a self-driving car. Like, the way that you would approach that type of problem from a kind of algorithmic design perspective is to kind of break it down into each of the kind of smaller problems that you need to eventually build a self-driving car. So things like we need to consider that kind of smaller sub-problems like, say, sensor data processing, route planning, control systems, etc., things of those nature. Okay, one application that's kind of listed here is in data science. So obviously in data science, you generally encounter problems where you're dealing with generally very, very large data sets. Usually you can't just take the data and analyze it straight away. Usually you have to do some kind of cleaning or some kind of additional step to kind of simplify the problem at the outset. So so as it says here, it says a large data analysis pipeline can be divided into data ingestion, cleaning, feature extraction, modeling, etc. And I guess, okay, that maybe it's not maybe necessary to emphasize this, but obviously the main benefit of doing problem solving this way is that it's generally easier to solve a problem once you've broken it down into lots of smaller sub problems rather than just trying to tackle it as a whole. Okay, so that was decomposition. So the next kind of principle is this so-called pattern recognition. So this kind of goes a bit more into the design of algorithms rather than decomposition, which is more about how you approach the problem. So pattern recognition is kind of based on identifying repeated structures, behaviors, or underlying themes within or across problems. So so I guess, yeah, the main motivation behind this is that generally there's certain problems which have solutions that are applicable across many different domains. So you know, I guess an example here is that many tasks in things such as engineering, i.e. feedback control, follow similar mathematical structures to other things. So if you're able to solve a problem in one context, you could potentially apply that solution in a slightly different context. Okay, another example here is it says that in mathematical physics, so recognizing that wave equation and certain heat transfer equations share similar forms that allow you to kind of apply the same solution. So if you know the solution to one type of equation in the context of heat transport, this may allow you to solve a similar type of problem or a similar type of equation that's applicable in a completely different context. Okay, and then benefit, again, probably goes without saying that this is kind of mainly to do with efficiency. Obviously, we don't want to be constantly reinventing the wheel. If we already have a solution to a problem, then we can obviously reuse it in a slightly different context. Okay, so the third is abstraction. So this is perhaps more important in the context of things like, so like in sciences, so physics, biology, chemistry, these types of things. So it's about taking a problem and kind of framing it in an abstract way. So in other words, kind of simplifying the complexity by focusing on essential aspects and kind of ignoring kind of unnecessary details. So, you know, in the context of physics, say you want to, I don't know, model the trajectory of a say I have like a tennis ball and I throw it and I want to model the trajectory of that tennis ball. In principle, you could treat that as an incredibly complex problem. You could model things like air resistance. You could model things like the spin of the tennis ball. In quite a lot of contexts, that's kind of unnecessary detail. You can just simplify the problem and assume that essentially I just have a point mass that follows a parabolic trajectory. And in most cases, that will give you a good enough solution without adding this kind of extra unnecessary detail. So, okay, another perhaps example of this is also in modeling things like population growth. So we can, you know, model population growth using a single variable for population size, while kind of ignoring other types of factors like age distribution, spatial location. Obviously, we have to be kind of quite judicious in what details we actually ignore, because there's going to be some aspects that are much more important than others. Yeah, and okay, a benefit perhaps I don't have to say is that obviously the benefit of abstraction is that it kind of helps us simplify things and solve problems more efficiency. So I guess the overall thing I'm trying to emphasize with each of these kind of core principles of computational thinking is they're mostly centered around simplifying things and making solving problems more, or trying to improve the efficiency of how we solve problems. Okay, and so the last is kind of algorithmic design. And so so this is about kind of crafting step-by-step procedures to solve kind of subproblems. So I mentioned with decomposition, we take a problem, we kind of break it down into smaller, kind of more easily solvable subproblems. And so once we kind of have done that, we can then potentially design algorithms that solve each of these subproblems, and then doing so thereby solve the problem that we were originally interested in. So okay, that gives an application of this in computational fluid dynamics. So one kind of algorithmic design that's important there is in numerical integration of certain differential equations in fluid dynamics. Okay, so I mentioned that that we would consider kind of one example. So I've kind of illustrated these ideas to you. What I want to do now is kind of just go over a very basic example and try to maybe highlight in a particular context how we can apply each of these you know, notions of computational thinking. So okay, we can look at how we can write or, you know, design a very, very simple algorithm for computing what's called the Leibniz series. So this is essentially a series for approximating pi up to a certain number of decimal places. So formally, you can show that pi can be represented by the series here. So maybe I can just go into a bit more detail, the derivation of this identity. So you can start by noting that pi is essentially 4 times the inverse of tan, evaluated at 1, which you can rewrite in terms of the this integral here. You can note that, okay, this integral is taken on the interval between 0 and 1. You can note that in this interval that that we can expand this fraction as a geometric series. So if you for terms which are of this form, where so for those of you who encountered geometric series before, you might know that. So if you have something which is the sum of a times r to the power of k, where a is just some constant and r is some kind of fixed ratio between terms, then it can be expressed in this form. So essentially, this is just the geometric series. And so here, what we do is we expand this up to a finite number of terms n, and then what we can do is once we have this expansion, this geometric series expansion, we can we can just substitute it into here to generate this expression, where this r kind of represents a kind of remainder term, which depends on n. So it depends on the number of terms that we include in our geometric series. This first term is kind of quite easily computable. So what we'd like to do is analyze how this series, or in particular, or more specifically, how this remainder term behaves in the limit that n becomes very large, so when n goes to infinity. So what we can do is we can kind of upper bound this remainder term in the following way. So we can note that since 1 plus x squared is always greater than or equal to 1 on this interval, so between 0 and 1, then we can note that this remainder is going to always be upper bounded by, or actually, so let me say that we first can evaluate this relatively, we can note that this, using this identity, that this is always going to be less than or equal to this. And then what we can do is evaluate this integral, so the integral between 0 and 1 of x to the power of 4 plus 2, which is just this 4n plus 3, x to the power of 4n plus 3. We can again use the fact that in this interval between 0 and 1, this numerator is always going to be less than or equal to 1. And so then we get this last identity, this last kind of inequality. And then obviously as n becomes very large, this term is just going to become very small. So more formally, that as n, this is going to go to 0. So this just tells us that as n becomes very large, this remainder essentially goes to 0. And then that leaves us with essentially an infinite series representation of this integral. And so then that essentially gives us our Leibniz series here. And so what we'd like to do is, so we have this kind of this formal expression for pi, which is practically speaking, interesting but not so useful, since it's an infinite series. It's not possible to compute exactly in practice. So what we would like to do is to come up with some kind of algorithm or way of essentially approximating this series up to a finite number of terms, and seeing how this series behaves as we go to higher numbers of terms. So how we can come up with increasing accurate approximations of pi using this series, or in a more mathematical words, the kind of the convergence properties of this series. Okay, so this is kind of the first bit of code that we have. So this is kind of an example of how you would write something that approximates pi up to some finite number of terms here, which is called num underscore terms. And so here what we have is some kind of function. I'm not sure if you did functions last week. Did you do functions? Okay, so hopefully some of this is kind of familiar. So yeah, what this is essentially a function that takes as an input the number of terms that you want to approximate pi up to using this Leibniz series. So so we start as pi, well, we start with 0, and then what we want to do is so you can think, so if you think about the formula we have in the previous slide, you have is essentially a sum of terms. What you want to do is to come up with some kind of function that iteratively performs additive operations. So if we want to sum up to 10 terms, so where number of terms is 10, what we do is we start with the first term in the series, then add to this the next term, add to this the next term, all the way up to the total number of terms. And so how can we do this in Python? We can do this quite easily using a for loop. And so what you do is you start with, well, you define this variable pi_approx as being 0. And then for each term in the series that you want to sum up to, so for k in this range, you essentially iterate over each of these terms, adding them each time to the initial value of pi_approx, which is here 0. And then, okay, you also multiply this by 4. So if I just quickly go back to the previous slide, this expression here should have a 4 in front of it. So if you just look at this expression up here, what we're doing with this function is we're just at each iteration in this for loop, we're just taking one term from the sum, evaluating it at a particular k, and then adding it to our previous value that we computed, and then multiplying that by 4. So hopefully that's kind of a bit intuitive what we're doing. Okay, and then this just defines a main function that just gives us an example of doing this for different numbers of terms. So we have here a list of integers that just basically that we can plug into this function, and then we can check to see how our approximation of pi improves as we increase, as you would expect, as you increase the number of terms, the approximation of pi improves. And so this just here gives you, I mean, you can, I think these notes will be uploaded onto the canvas. So if you want to take this code and play around with it yourself, then feel free. So this just shows you an output. If you just run this script, this just gives you the corresponding output. So it starts by evaluating the series at a single term, 10 terms, 100 terms, etc. So up, essentially increasing the number of terms by a factor of 10 each time. And you can kind of, as you would kind of naturally expect, the more terms that we incorporate into the series, the better the approximation of pi becomes. So again, this is maybe a bit of an overly simple example, but how did we kind of, how do we apply our kind of core principles of computational thinking here? So what we did is we started with this kind of expression for pi, and then what we wanted to do is to come up with some function for evaluating pi. So what we had to do is kind of break it down and say, okay, well, we can, so if I just go back, sorry. So the decomposition part is here, taking this entire series, breaking it down term by term, and then coming up with a function where at each step, we just evaluate one term in the series, and then we add it on to the next term. And so you can kind of maybe also say that here the pattern recognition is the aspect that at each iteration, we're just doing the same thing. We're just evaluating each term in our sum and then just adding on to the previous one. So this is kind of maybe not the best example for illustrating these principles, but it's just kind of meant to be a kind of hopefully somewhat intuitive. It's meant to illustrate in a somewhat intuitive fashion how you can kind of apply these ideas to come up with something that something that in a sense uses these principles to compute something of interest. Okay, so yeah, what I thought, I don't know what the previous format of these lectures has been last week, but what I thought now is it would maybe be good if we could try doing a kind of more hands-on thing. So I wanted to maybe give you an opportunity to try to write your own kind of mini scripts in Python to compute like the first Fibonacci numbers, which is kind of, building off what I just showed you with approximating pi. So taking the same principles that I showed you there and then trying to use them to come up with a way of computing Fibonacci numbers. Is that okay? So maybe we can try to spend like, I don't know, 15, 20 minutes doing that. That's okay. Cool. So I'm assuming that for those online, that's okay as well. Hi, so yes, welcome back. Sorry, we had quite a bit of a break just for that exercise. So hopefully you made some progress. I think what we were trying to figure out was to how we can post the code onto the Slack channel. So I think there were some questions regarding the previous code that I showed. So I think we're in the process of trying to get that code onto the Slack, or to also get these slides onto the canvas. So hopefully you should be able to access the code on either of those two either of those two areas. Okay, so so maybe for the remainder of this lecture, what I'll do is I'll just quickly outline the solution to this exercise, and then afterwards we can maybe go into a break. I'm not sure what time we usually break, but yeah. So I think that the plan at the moment is to finish this exercise, and then we can have a break after that. Okay, so the exercise that you had was to compute these first the first n Fibonacci numbers. So essentially we have a kind of recurrence relation. So if you start from the 0 Fibonacci number f0, which is 0, and knowing that f1 is 1, then the idea, what we wanted to do is to write down design a very basic algorithm using these kind of 4 computational principles that I outlined previously of how we can compute this Fibonacci sequence for any for any number n greater than 2. Okay, so this is one solution for doing this. Oh, wait, hang on. I think this is the wrong bit of code. Hang on, let me just, sorry, this is like the wrong piece of code. Let me just change my screen, and then I can show you the actual piece of code. So let me just reshare my screen. Sorry about this. Okay, so hopefully you can now see my my terminal. So so this is the code here to generate the first n terms of Fibonacci sequence. So here I have some function that we call Fibonacci, which just has a single argument of n. So this is just the number of terms in the sequence that we want to compute. And we follow a similar kind of thinking that we did with the previous example I gave of the Leibniz series. So when we wanted to compute or approximate pi using the first n terms of this Leibniz series, what we did is we had some kind of recursive algorithm where we started from some initial value, and then what we did is iterated over a number of values, and at each step added the computed value to the current value of pi. So we started from a value of 0. We computed the first term of that series. We then added that to so we then redefined what our value of pi is according to that computed value, and then iterate again, add that value to the next, or add that value onto the current value of pi, etc., etc., etc. And then as we iterate further and further, we then build up an increasingly accurate approximation of pi. So here we're kind of following a similar logic, except now we're computing this Fibonacci sequence. So what we want to do is to also incorporate this condition that I had that we want to compute the sequence for n is greater than 2, greater than or equal to 2. So initially, so the first 2 terms of the Fibonacci sequence are f0 is 0 and f1 is 1. And so in this function here, we have this conditional statement that if n is less than 2, then we just return whatever the value of n is to, so this would correspond to either n is equal to 0, n is equal to 1, and this just returns the first 2 numbers in the Fibonacci sequence. So if n is greater than 2, or greater than or equal to 2, then what we have to do is to we then have to apply this recursion relation I had on the slide. So this is essentially what this for loop does. So what we do is we define some, we need to store at each step of this iteration the value of f of n minus 2 and f of n minus 1. And so this is what these two variables do, f of minus 2 and f of 1. So we initialize them as 0 and 1. And then to compute f of n for n is greater than or equal to 2, we then perform this kind of for loop. So this current value here just computes the f of n for the current value of n, and then it basically, and then in the next line, what we do is redefine what f of minus 2 and f of minus 1 are for the next iteration. So we essentially update. So once we computed f of n, what we then do is we redefine f of n minus 2 as f of n minus 1 and f of n minus 1 as f of n, and then we reapply the same operation. So this is the kind of the pattern recognition part of the algorithm, if you want to call it that. So this is where we can recognize that we can just perform the same sequence of operations however many number of times to generate the Fibonacci number.
Could you zoom
f of n.
in, please?
Hi, yes, sorry. So I heard somebody speaking. I'm not sure if they had something to say. Otherwise, I'll just carry on.
Yeah, sorry. Can you just please zoom in your screen? It's quite small.
Oh, sorry. Okay. Let me zoom in. Zoom. I'm not sure how to zoom. Things come to bonus.
Are you using a Mac?
Yeah, I'm using the Spider IDE though. I'm not sure how you can zoom in on that. I'm not sure if entering full screen. No, I don't think that would help.
So just right click on your editor. Or where
Sorry,
you're typing. Where you're typing the script, just right click there.
Right click, like this.
Yeah,
Oh,
I'm going to zoom in.
Okay, yeah, thank you.
Can you zoom in a few times?
Yeah, this hopefully is better now. Okay, hopefully that's a little bit better now. Okay, so yeah, sorry about that. For those who maybe it was a little bit too small. Okay, yeah, so we have this for loop which iterates over these two initial values of what we call f minus 2, f minus 1, and then at each point in this for loop, what we do is we compute f of n for whatever value of n we have here. So this is for n is greater than 2, so it goes from 2 up to the final value n. And at each point of this for loop, we store the current value of f of n, and then we update what our previous two values are. And then at each, and then we finally return whatever our value of f minus 1 is. Okay, and so this is the function. What this second part of the code does is it essentially implements an example of that. So if in this terminal, what I can do is down here is I can just run this code, and it will just show you. I'm not sure if I can also zoom in on this part. Okay, hopefully you can see this output from the terminal. Okay, so essentially what this does is it just calls this. So we have this for loop here of that just computes the first 5 terms of or actually 6 terms of the Fibonacci sequence. And so it just calls this function that we call Fibonacci 6 times. And so it just generates F0 all the way up to F5. And so what we can do is, if we so want, we can kind of play around with this and say, okay, let's put 20 here instead, and then run the same function. And then it generates now the first 20 terms of the Fibonacci sequence. Okay, and then you can, I should be able to put this code on either the canvas or through the Slack, and so hopefully you should be able to play around with this yourself, just to kind of complement your own understanding. Okay, so that was kind of an idea of how we can apply in a kind of very basic way these kind of computational thinking principles that I mentioned before. So let me just now go back to the slides I had. Okay, so let me just go like this. Oops, sorry. Let me just reshare. Yeah, this is the right one. Okay. So as I said previously, so the decomposition, so these 2 kind of computational thinking principles that I mentioned before, one of them being this decomposition, the other being abstraction. So in this Fibonacci sequence exercise, the kind of the decomposition part is being able to first divide the problem into these 2 smaller subproblems, in which we first compute f of n-1 and f of n-2. We then use these to compute some value f of n, and then we iterate. So we then redefine what these values of f of n and f of n-2 are, and then once we've updated these 2 values, we then use them to compute the next value in the sequence, and etc. And so to continue on to the final value. Okay, and so the abstraction part is maybe not so important here, since it's just a relatively basic problem, but I think the most important part here is this kind of decomposition of the problem into these kind of subroutines of computing f of n-1 and f of n-2. Okay, so I think I said that I'm not sure what the schedule, the intended schedule is, but I think that maybe what we can do is go for an early break now. So let me just finish up by saying, so at least in this first lecture, what the kind of the key ideas I wanted to kind of convey was the kind of 4 kind of main core principles of computational thinking, which is this decomposition, pattern recognition, abstraction, algorithmic design. So we kind of use these, but in a very simple way, in looking at an approximation of pi using a Leibniz series and the generation of these first m Fibonacci numbers. So in the next lecture, I think what we'll do is kind of go into problems that kind of more explicitly make use of these kind of core principles in the use of other types of algorithms. So ones which are a little bit more, I guess you could say, practically useful than the 2 examples that I gave in this lecture. Okay, and so there's also some recommended reading here if you're interested. So I think saying that, we can maybe go into a break. I'm not 100% sure what time to reconvene, but I can post into the chat, into the Slack, what time we intend to reconvene for the next lecture, if that's okay.
Hi, Graham, can you hear me?
Yes, I can hear you, yes.
So our break's at 11 o'clock, so we can break earlier, then we can continue at 11:15 again.
Okay, sure. Thanks.
Thank you.
Okay, hi everyone. Sorry for the delay. I think we can maybe proceed with the next part of the day until lunch. So let me just share share my screen again. Okay, I think you should be able to see my screen. Yeah, so what the plan is for the second part of the morning is to talk a little bit more about these computational principles that I introduced in the first part of earlier this morning, that we then partly used to look at two practical examples of how you could approximate pi up to a certain number of decimal places and generating an arbitrary number of terms in the Fibonacci sequence. So what we'll do is build on those ideas in this part, going to slightly more complicated or more complex practical examples. I should say that the structure of this talk is, so I'll go over some of the background behind these principles that I outlined again, and how we can apply them to slightly more complicated examples. The idea is to then give you another exercise. So I think I'll also illustrate some more examples. So we'll take the code. I'll take the code that I will show here and put it onto the Slack channel, like we did with in the first lecture. And yeah, the idea is to then give you an exercise so you can get kind of more practical experience in working through this kind of computational thinking. Okay, so let me just maybe recap very briefly what we did. So I introduced these thinking principles. So these computational thinking principles. So they were decomposition, pattern recognition, abstraction, algorithmic design. So decomposition being, we want to take a problem, we want to break it up into many smaller problems, and thereby, if we're able to solve each of these smaller problems, this will then enable us to solve the problem as a whole. Generally, this is easier to do than trying to tackle the problem head on. Pattern recognition. So if we're able to perform a particular step, we can repeat the step many times to potentially solve our problem. So we looked at that in the previous practical examples of approximating pi and the Fibonacci numbers. The abstraction, which we didn't really do, but that's more to do with if you have more related to things like more scientific related or mathematically related problems. So if you want to model like a dynamical system or something, you generally want to simplify that model enough that it keeps the enough detail that you're able to describe the underlying behavior of that system well enough, but without adding too many unnecessary details to the modeling. And all these three ideas then go into generally algorithmic design, how we design our algorithms to solve the problem at hand. Okay, so what we'll do now is think more about looking at some other types of examples. We'll build more on the ideas of decomposition and algorithmic design. And so the decomposition, as I said, was taking a problem, generally large or complex task, and seeing how this can be systematically broken down. And I'll look at some kind of common kind of algorithmic strategies where this is relevant. Okay, so I don't think I need to recap these computational thinking principles again. But what we'll do is go into overviewing some like greedy divide and conquer and kind of dynamic protocoling approaches to this kind of decomposition as part of the computational thinking that I mentioned. And then, as I said, we'll look at the kind of practical code demonstrations of Python, like I did with the previous earlier this morning. So we'll give you this code. I'll try to I'll make sure that the code will be put onto the Slack channel. And then towards the end, we can look at maybe a worked example of this kind of so-called quick sort algorithm, and then also give you an exercise that you can try having a go at yourself. Okay, so okay, I don't think I need to go over that again. Apart from just emphasizing again that this decomposition idea is that we take a larger complex task and we want to generally decompose it into a much smaller set of problems. And so there's kind of two general ways of doing this, two general approaches to this decomposition. One is this so-called top-down decomposition. So we start, as we always do with the entire problem, and then we want to break it down to finer sub-problems. An example of this being, so if you want to develop a data analysis pipeline, you first kind of outline the major phases. So, okay, like data ingestion, cleaning, feature extraction, modeling, visualization, and then delve into each of these kind of subtasks. So the bottom up is kind of the opposite of this, where you identify the smallest or most fundamental tasks and then combine these to build up into to compose like the entire solution. So again, okay, it gives here an example. So in software, you might build and test valid data structures or helper functions before assembling them into a final application. Okay, so why these two types of decomposition matter? Well, for large systems, so an operating system, simulation of climate change. So generally these types of systems are too complex to just treat as a whole. Generally, you're generally in a way forced to break these types of systems down into smaller sets of problems, rather than working a single kind of monolithic block of instructions. So collaboration, so if you're in team-based projects, so sub-modules can be assigned to different individuals or groups. Debugging and testing, I guess, decomposition matters in this context. So I guess that this last point kind of was more applicable to the bottom-up approach to decomposition, so that I mentioned here on this slide. So again, this is kind of a very generic introduction to these two kind of approaches, but so hopefully it'll come a little bit more clearer as I go through this, as I go through the lecture, what I mean explicitly by this top-down and bottom-up approaches to decomposition. Okay, so talking in more kind of maybe explicit terms now, so is considering these two approaches to decomposition, we can kind of classify these kind of algorithm approaches in at least kind of three ways. So we can classify them as like kind of greedy algorithms, divide and conquer algorithms, and dynamic programming. So what I'll do is I'll kind of go over each of the definitions of these three things. So a greedy algorithm solves a problem by making the locally optimal choice at each step, under the kind of the kind of a priori assumption that these local choices will lead to a kind of globally optimal solution. So I guess in other words, what you do is you break down the problem, you do a decomposition of the problem, you then focus on each of these kind of subtasks, you solve each of these subtasks in an optimal way, and then you kind of make this assumption that, okay, if each of these subtasks are optimized, then this will, by extension, optimize the entire problem that we want to solve. This isn't always true, but it's a kind of generally it's an assumption that works well for many types of problems, as I'll kind of show with an example. slightly later. And so why are greedy algorithms interesting, or why are they important? So I guess for simplicity, generally it's easier to optimize smaller scale problems and then replicate this across many other kind of subproblems rather than try to optimize the entire problem as a whole. And generally they tend to be more straightforward to implement and more faster to run. When they work, so I mentioned that there are some problems where this doesn't work, where optimizing each of the subtasks doesn't necessarily give you a kind of global optimization of the problem. And so so when they work, so certain problems, for problems where this kind of greedy approach algorithm works, we call them greedy choice. We say these problems have a greedy choice property, meaning that the local optimum selections lead to a global optimum. So there are some problems that we call greedy choice property that are amenable to these types of algorithms. There are other types of problems which don't satisfy this property, where these types of algorithms don't really work as well. Okay, and so when they fail, so yeah, as I said, so not all problems are amenable to these types of strategies. Typically, the structure of the problem itself reflects whether a greedy algorithm will be successful or not. So some common examples of greedy algorithms. Again, these are just kind of 3 examples that I've thrown out. I'll also go into a slightly more detailed example where I'll show the code as well to kind of illustrate a bit more clearly where these types of algorithms work. So just to kind of mention these examples, one is this kind of interval scheduling. So we select the maximum number of non-overlapping intervals by repeatedly picking the interval that finishes first. Another one is minimum spanning tree, or MST. So these are algorithms like Kruskal's or Prim's. So adding edges on nodes in a loop. Okay, I think this applies to graph theory. So in this context, that adding nodes in a locally optimum fashion, you can use this to form a tree of minimal total weight. And then, okay, Hoffman coding, repeatedly combine the 2 least frequent symbols to build an optimum prefix free code. Okay, these are kind of generic examples, but as I said, I'll go into something a bit more explicit in the next few slides. So this is now like an explicit example where we can use this kind of greedy algorithm approach. So this is a problem that we can say has this kind of greedy property. So consider like the following problem. So say this is a kind of formal way of putting it, but the idea is that what we want is if we have some kind of a given amount, which is like some positive integer value. So this could be like 10, 100, 1,000, etc. What we want to do is find a set of smaller numbers, and then with each kind of number in this set representing how often a coin of a particular value is used, which minimizes total number of coins. So the idea being that you pay for something, you get given a certain amount of change back. What we want to do is find with a particular set of denominations that are represented in this set, what's the minimum number of coins that we need to use to be able to give back a certain amount of change. So this amount of change is represented by this number W. Okay, so we have some kind of optimization problem where we want to minimize, with a particular set of denominations, we want to minimize the total number of coins that makes up this value. Okay, so kind of formally, this problem is stated in this way. So we have this function, and we want to minimize the total number of coins n subject to this constraint. Okay. And so why does this problem satisfy this kind of greedy criterion? So what we can do, like one kind of strategy for solving this problem, is to just always use the largest coin denomination possible at each step, and then repeat until the remainder, with the remainder until it's 0. So the idea being, if we are given a certain set of denominations, like say, I don't know, you have a coin of value 1, a coin of value 5, a coin of value 10, and you have a certain amount of change you need to make up, what you do is you pick the largest value in that denomination, see how many times it goes into the total number, and then keep going until you're no longer able to divide that number by that largest denomination, and then you go to the next smallest denomination, etc., etc. And so this is an example where this this kind of greedy algorithm works, since that strategy tends to be the optimum strategy. Okay, so and this, okay, this is maybe a little bit more something worth noting is that so this approach works optimally if the coin denominations follow certain patterns. So it doesn't work for all types of coin denominations, but certain types of coin denominations, like, for example, I don't know, like the US dollar, or I guess I'm not sure the names of all the coins, but I guess you have like a cent, a nickel, a dime, etc. So it works for these types of denominations, but for arbitrary denominations, this type of strategy doesn't always work. Like either type of the strategy where we always just pick the largest denomination, see how many times it goes into this value, and then repeat until we cover all denominations. Okay, so this is kind of like the broad overview of the problem. Here's like an example of some code that you might want to, that you could use to solve this type of problem. So, so as I said, so that what we have is we want to make change with a known set of coin denominations. So this is an example which applies to, I guess, a case of like, US currency, where you have quarters, dimes, nickels, pennies, where these correspond to these values respectively. So, a quarter of a dollar, a tenth of a dollar, 20 of the dollar, etc. Okay, so what we have here is a let me zoom in if it's too small. Maybe it'll be a bit easier if I zoom in. There we go. Okay, so hopefully that's a little bit easier to see on your end. Okay, so so we have a function here that takes as input the total amount in change that we're given, or the change that we need, and the set of denominations, so each of these values. Okay, and then what we want to do is we return a list of coins that sum to the amount. So basically the number of the corresponding denominations that make up the amount of change. So this could be, for example, 2 quarters and a single dime if we had a change of 60, or 3 nickels and a dime, etc., etc. So we have a function that returns a list of the corresponding number of coins that we use to make up our change. Okay. So obviously these are integers, so these inputs are integers. So it's the number of coins that we, or the amount and the denominations are integers. Okay, and so what we then want to do is, from what I outlined on the previous slide, is that we want to find out the smallest number of coins that make up a particular amount, subject to a particular constraint. So we start by defining our result, which is this list that contains each of these number of coins corresponding to each denomination, and then what we do is then take as the amount is an input to this function here, which is passed to this variable remaining. And then we do is, so this is the kind of greedy algorithm approach, where what we do is we just go over each of the coins containing denominations and say, while the amount remaining is greater than the value of the corresponding coin, then what we do is we just append this coin to the list. So this is essentially doing what I mentioned previously, where you pick the largest coin denomination, you then keep adding this until you get to a point where if you add it and you exceed the total amount of change, then you can no longer use that denomination. So then you have to go to the next smallest denomination. So this is essentially what this while loop is doing. It's just iterating over all the denominations contained in this list here as an input. Okay. Okay, and if the remaining is never zero, then this greedy approach doesn't work because you can't form the exact amount of change. Although for this problem, it should be viable since we always have a 1 denomination, so we can always make, if the input is an integer value, then we should always be able to make it out. Okay, so this is just a function, and then what we do here is just an example of an application of this code. So where we specify our denominations in descending order. So this, just to mention also that this function works on this assumption that you pass the denominations in highest to lowest order, and then we specify a certain amount, and then we run this function in the following way, and then it prints out essentially the change for the certain amount with the corresponding number of coin, or the number of coins corresponding to each denomination. Okay, so this code will be put onto the Slack, so you can look at this yourself. You can play around with this yourself to make sure, you know, to see the intricacies of how it works. So I think I have an output listed on the next, if I'm able to move. Yeah, so if you run this code, an example, if you use an example of, if you have change of 87 cents and you have these denominations, then what this function then does is just outputs this list. So this just gives you it gives you the number of coins used. So here we have 3 coins of denomination 25, and then a single coin of denomination 10, and then 2 of 1. And so this generally, as I said, for these types of problems, this satisfies this greedy property because we can always pick we just start by picking the largest denomination, keep adding it until we get to a point where if we exceed the total value, we then go back down to the next leading denomination. So in this example, we start with 25. We want to make up 87. So we start with 25, add another 25, that makes 50, add another 25, that makes 75. At this point, we can't now add another 25, because if we add another 25, this will put us at 100, which is obviously over the total amount of change. So then we have to go down to the next denomination, which is 10, you add this, and then et cetera, et cetera. And this generally gives you an optimum. This doesn't universally give you an optimum solution, but for most types of denominations, it does give you an optimum solution. Okay, and so this is maybe kind of extra detail. One thing to kind of note is that what we call kind of time complexity. So what I mean by time complexity is that if our input is of a certain size, like how many kind of coin denominations we're using, generally how long does our algorithm take to run? How does this time scale with the size of our input? And so if there are m denominations, in general, this type of approach, we have to iterate over all of them. So in this example I gave here, we have to iterate over every type of coin denomination once to actually make up the total. And we have to take into account that each coin might be used more than once. So what this implies is that the worst case scenario is roughly the time complexity, the number of denominations times by the input amount over the minimum denomination that we have. Okay, I mean, this is a more technical point. This is just something to note. I won't go into too much detail about this. Okay, so as I mentioned, like for most problems of this nature, this type of approach usually works. So I guess you could say for, I guess what you call canonical currency systems, like real world currencies, where you have a 1 coin, a 5 coin, a 10 coin, or something of that kind of nature. Then it's possible to show that this approach guarantees you to find an optimum solution. if you have kind of arbitrary denominations where you have ones which don't have this kind of same structure, but you could have, say, e.g. 1, 3, 4, then it doesn't always give you an optimum solution. I guess that's kind of a reflection of the fact that in reality, we tend to introduce denominations. The denominations that we choose to structure our currency tend to be ones in which we can find optimum solutions to giving change. Otherwise, it wouldn't be a very good currency system. Okay. And so, yeah, maybe just to mention in a bit more detail why this problem, how this kind of a greedy choice property is reflected in this type of problem. So that's for the reason that, so this problem exhibits this property of choosing the locally optimum coin never blocks reaching a global optimum. So in this case, it didn't, since we could always just start by choosing the largest denomination and then going to the next denomination, and it never, we never got to a point where with the remaining denominations, we weren't able to reach the global optimum, which in this case is the exact change, which is 87. Okay, this is kind of a little bit more complicated, but talking about how you can actually prove this. So proving this typically involves an exchange argument showing that any optimum solution can be transformed into one that starts with a greedy choice. Okay, so these are kind of just additional notes. Like, I think hopefully I can kind of convey this kind of idea of this kind of greedy approach to algorithms where we take a problem, break it down, and then we choose a particular optimum strategy that works kind of locally or works well in one instance, and then we just repeat that strategy under the assumption that it will optimize the global solution as well. Okay, so this is kind of like a summary of this example of the greedy algorithm is that they one of the kind of advantages is that they're often straightforward and to implement. Usually the approach is kind of the most intuitive approach to use. Like in the coin example, intuitively, if you just start with the largest and then you keep going until you can no longer use that coin and then go down, that tends to be the most intuitive way rather than just randomly choosing coins. And so these types of greedy approaches or greedy algorithms can be quite very successful, but the success depends heavily on whether the problem has the right structure. I won't kind of elucidate too much on this, but it's just kind of worth bearing in mind that this type of approach doesn't always work. It's not always the most optimum approach. But saying that, even when optimality isn't guaranteed, these types of algorithms can still provide relatively fast approximations in large-scale problems. So they can kind of be used as a way to gain insight into the problem without necessarily giving you the most optimum solution. Okay, so those were kind of, that was one approach, this kind of greedy algorithm approach to kind of problem decomposition. So now we'll kind of talk about a little, now a different approach, which is this so-called divide and conquer algorithm approach. So as I said, as before, let's just start with a kind of definition of what this divide and conquer algorithm is. So a divide and conquer algorithm breaks a problem into smaller subproblems, so decomposition that closely resembles the original problem, and then solves these subproblems essentially recursively, and then combines their partial solutions into a final answer. Again, this maybe seems a little bit non-intuitive, but I'll illustrate with an example which hopefully conveys a little bit more clearly what we mean by exactly by this. And so, yeah, this approach is effective when so each subproblem can be solved independently. Okay, so maybe just to emphasize each of the parts. So the divide part references the fact that we partition the original problem into these subproblems, and then what we do is that once we have this division into subproblems, we then recursively solve each of these subproblems and then combine each of these to essentially solve the original, the problem that we originally wanted to solve. Again, this is kind of a bit of a generic explanation. Hopefully it'll be a little bit clearer in the next few slides. So the advantage of this type of approach is that it tends to work well with kind of parallelization. Again, the fact that you're able to break a problem down into smaller subcomponents generally reduces complexity, makes it a bit more tractable. There's kind of quite well-known examples that follow this pattern. So for those of you who maybe know already, so there's this merge sort algorithm, quick sort, binary search, and fast Fourier transform. Okay, so those advantages, some kind of drawbacks. So it repeatedly performing this kind of recursive procedure can introduce kind of additional overhead. And trying to combine each, recursively solving each of the subproblems and then trying to combine these can also be, in a sense, non-trivial. And yeah, okay, it's not always straightforward to design the divide and combine steps optimally. Okay. So okay, that was kind of like a generic explanation of what this divide and conquer algorithm is. Here's another example of where we can apply this type of approach to the so-called merge sort algorithm. So this merge sort algorithm is an algorithm that so sorts a list of elements in ascending order. Okay. Again, here's some. So this is not Python code like I showed before. This is kind of what we call pseudocode. So it's just code that kind of in a kind of heuristic way reflects what this algorithm is doing. And so what we do with this merge sort algorithm is we define a function that we call merge sort, which takes as input this list that we basically want to sort in ascending order. And so the divide approach is that we say that if this input list is of less than this is just a kind of conditional statement that makes sure that we're inputting a list which is of greater than length 1. I mean, trivially, if you have a list of length 1, it's already sorted in ascending order. So this just outputs the same lists that you input if it's of length 1. But generally what you do is with this kind of divide and conquer algorithm with this merge sort is that you take your input list, divide it into 2 lists, sublists, so each of half the length of the original. And then what you do is you sort each of these 2 sublists and then combine the 2 results. And then repeatedly applying this kind of sort to each of the sublists will eventually then give you an output list that is the same length as the input with whose elements are in ascending order. Okay, so this kind of first function repeatedly applies this kind of division into multiple sublists. So as I said, you input a list, you divide this initial list into 2 sublists, and then you keep repeating this recursively. So then you take these sublists, divide them again, etc., etc. You keep going until you essentially can't divide these lists any further. And then once that's implemented, you then run this kind of merge function, which is just below here. So what this merge does is it then basically goes through each of the sublists that you generate from this first function, and it basically just compares each of the elements in each of these lists, or it compares kind of nearest elements in this list. So say you have an initial list of 4, length 4, it breaks this down into 2, and then it breaks these 2 lists into 1s, and so you have essentially 4 digits. And then what you do is you compare each of these compare one digit with its neighboring digit, and then you check to see is one larger than the other. And if it is, you then swap them. If it isn't, you keep them in place. And then what you do after you've done this kind of sort on each of these sub lists, if you call them that, you then combine them again, which is this this second part here, and then you essentially output the result. And doing this repeatedly, so comparing these or breaking it down into your initial list into these sublists, sorting each of the neighboring indices, and then recombining them, eventually will give you an output, which is a list of the size of the original input in ascending order. Okay, so again, this is kind of pseudocode, so maybe it's not exactly 100% clear. What I'll do is I'll also, like the other code, put this onto the Slack. There are also examples of this kind of merge sort algorithm. There's examples of this code online as well. So if you're interested, you can also look at specifically Python code that performs this type of merge sort algorithm. Okay. Okay, so then just to finish up with this kind of divide and, so that was an example of a divide and conquer algorithm. So again, just to kind of re-emphasize the process with this example of a merge sort, what you do is you recursively split the list into two halves until each of the sublists have at most one element. And then you sort each kind of smaller list. And then you combine each, by comparing neighboring digits in each of these sublists. And then once you've sorted all these sublists, you then combine all them together, and then that will give you a list which is of length n, which will be in ascending order. Okay, and again, complexity, this is kind of an additional detail. The time complexity is on average how long does that algorithm take to run based on the size of the input, and this kind of scales in this way. So with n, there's the size of the input list. So it's kind of scales kind of logarithmically, and the space is to do with the kind of the space complexity is to do with the memory. So this scales kind of linearly in the size of the input. Okay, these are kind of just additional details if you're interested. Okay, so another example of this kind of divide and conquer algorithm is a so-called quicksort algorithm. So this is kind of similar to this kind of previous merge sort algorithm. So in the sense that we want to take a list of n elements and sort them in ascending order, but use a kind of what you call like in-place partitioning. Okay. I think so. What we do here is we set some variable, which is this kind of partition index. And then what we do is we kind of recursively sort these elements before and after this partition. Okay, so this is just, again, this is just a pseudocode. This isn't specifically Python code. There are examples of this quicksort algorithm that you should be able to find online, which implements it specifically in Python, which follows this kind of pseudocode, which follows the same structure as this code that I'm showing here. Okay. And so, okay, I'll also put this code onto the Slack. I won't go over too many of the additional details, but this is something that you can also, if you're able to find examples of this Python code online that performs this quicksort, then this is something that you can also implement yourself, and to check to see that the details of how this works in comparison to the merge sort algorithm. So this kind of quicksort is essentially an amended version of this merge sort algorithm. Okay. So again, this is just a kind of explanation of what this kind of this quicksort algorithm does. So the divide element is that we choose a kind of a pivot, which is the last element of the list that we input. And then we partition the list so that all elements which are less than this pivot are on one side and all that are greater on the other. So this is slightly different from the merge sort like I gave previously, where we just divide the list in the middle recursively, whereas here we explicitly choose a pivot to perform this division. And then the concat aspect is the recursive application of this kind of quick sort to each of the sublists on either side of the pivot, and then combine, and then the final part is the combination at the end. So you then output a list which is of length n in ascending order. And so the complexity in this is, again, similar to the merge sort algorithm. So it's kind of logarithmic. The space can have a slightly better scaling than the merge sort, in that although this is a kind of represents a typical average scenario case rather than a worse scenario case. But again, these are kind of additional details if you're interested. Okay, I'm not sure how what time, just to clarify, what time are we planning to break for lunch, just to make sure. If anybody can mention in the chat, that would be quite helpful. Okay, I can't hear anything on my side, so I'll just keep going until someone mentions that it's time for the break. Okay.
Graham said 12:30.
12:30. Okay. Okay, 12:30. So maybe okay, I'll go over another example of this divide and conquer algorithm, which is this binary search, and then what I think I'll do is I'll get to the exercise. I'll stop just before the exercise, and then maybe afterwards we can pick up with that exercise. Okay, so this another example of a divide and conquer algorithm is this binary search. So the goal is that so given a sorted array and a target value, we want to determine if this target exists in the array. And so if it does, then we want to return its index value or return an indicator that's not found. Again, this is kind of example of pseudocode, which gives an indication of what this algorithm does. So let me try and zoom in again. Okay, so we have a function that we call binary search. We take as input into this function the array that we want to examine, the target value, so the value that we want to find in this array, and then these two additional inputs that we call left and right. So the idea of this binary search is that what we do is the binary aspect is that we take a list, we basically divide it to two, and then we search each of the two smaller parts of this list for the target value. So this is what this left and right input basically does. So we say if left and right, if left is okay, this is just a conditional statement that says if left is greater than right. So if we take our input array, if we split it, if the left side of this array is larger than the right side of the array, in that it contains more elements, then we basically return -1, which is this indicator that the value wasn't found. Okay, and so this essentially is the thing that kind of terminates this algorithm. So what we do is we define a midpoint, which is essentially what divides this our input value input array into two parts. We then we look at the value of the rate at this midpoint. If that matches our target, then we've already found our target, and then we output this midpoint. If not, then what we do is we search each of the two sub-arrays, so the left and right parts of the array that we split using this midpoint. And so then we kind of we recursively apply this binary search to now this the left array and to the right array, and then we continuously do this until we basically find until either we find an index, the target value in each of these two subarrays, or we don't, this target index isn't found, and then we return a value of -1. Okay. So I guess, intuitively, you can see how this represents a divide and conquer, since it relies on basically taking an array and dividing it into two parts. So we split the array into two halves at a midpoint. The algorithm then works by kind of recursively searching the half of the that may contain the target and disregarding the other half. So I should have maybe mentioned, actually, sorry, that in the search, you split your array, and then you look at one side of the array first, and then you search that, and then if not found in that part, then you search the other half, and then you repeat, basically. So and so the reason why this is, you could ask the question, okay, why, if you want to do a search, why don't we just linearly search? If we just start at the first element, look at the first element, then go to the next one, and then keep going until we find the element, why don't we do this approach rather than using this slightly more complicated? The answer to that is that because this approach is generally faster than the other one, since unless you have very special cases where the element that you're searching for in your array is at the very beginning of the array that you start searching it from, generally speaking, it will take longer to do it this other way. So this kind of binary search represents the kind of the optimum approach in the general case for finding a target element. Optimum in the sense that it minimizes the time complexity. So it scales as log n rather than n. So the alternative that I gave, where you just start from the first array element of the array, you check that, and then you move on to the next one, you go through all the elements. This scales linearly with the number n, whereas this case it scales with the log of n, so it's slightly more efficient in the average case. Okay. And so, okay, so those were some examples of this kind of divide and conquer strategy. So it's a strategy that underpins quite a number of fundamental algorithms. And so, yeah, the merging partial results can be the most integral aspect of the algorithm. Okay, these are points that are more specific to this merge sort that I mentioned, or the second sort algorithm that I mentioned, the quick sort. So so in the quick sort, the pivot selection and deciding which half to explore in the binary search are kind of the critical to the performance. Okay. Okay, so we have a little bit more time. So maybe what I'll also do is now go into dynamic programming. And then hopefully we'll be able to finish just before 12:30, I think. Okay, so dynamic programming. So I can give the following definition of dynamic programming. So dynamic programming is a strategy that systematically saves and reuses solutions to overlapping subproblems. By avoiding redundant calculations, dynamic programming can transform exponential brute force solutions into polynomial time algorithms in many scenarios. Okay, that's quite a high-level definition of dynamic programming, but again, I'll illustrate this with a particular example. Okay, so again, I'll just go through this. So key concepts of dynamic programming is that is this idea of optimum substructure. So a problem exhibits optimal substructure if its optimum solution can be constructed from optimal solutions of its subproblems. So, okay, an example being the optimum solution to the large knapsack instance is built from, okay, that's an example of a type of algorithm. So dynamic programming is most beneficial when the same subproblems occur multiple times. So in the example that we gave previously with this Fibonacci sequence, this can be performed recursively in the sense of that the 10th element of the Fibonacci sequence depends on F9 and F8, and F9 depends on F8 and F7, and so on and so on. And so therefore, we have overlapping subproblems in this example in the sense of we're computing at each step in, say we want to compute F10, we have to know what F8 and F9 are. But we know these from our previous step where we calculated F9 from F8 and F7 and so on. So we're essentially reusing the same, reusing previously calculated elements in the sequence to then generate other ones. So in a sense, like there's an overlap between what you calculated and then what you use in subsequent iterations of this Fibonacci example. Okay, okay, I won't maybe go too much into this, but so memorization and tabulation again. I think it's probably best just to skip this bit, but that's okay. So so some examples of dynamic programming. So we already looked at one, which was this Fibonacci sequence that I gave earlier. So a kind of a bottom-up approach to or the use of dynamic programming in this instance cuts the naive exponential recursion to order n. Again, these are some other examples of dynamic programming. They might not mean as much to you as this Fibonacci example that I gave earlier, but I would mention them anyway. So this like NITheSat problem. So so maximizing the total value under a weight constraint runs as order to n times w, and w is a capacity. So I think the knapsack problem is where you have a certain number of objects of a particular weight, and you want to kind of perform some kind of optimization. Okay, but I won't go into too much detail about it. But another example of this dynamic programming is the shortest paths. So finding distances between all pairs of vertices in a graph, and this has a time complexity of order n cubed. Okay, I think this is maybe a little bit too overly technical, so I think these will be in the slides that are uploaded to the Canvas. So if you're interested, you can obviously take a look yourself. I think it's maybe a little bit overly technical to go into now, so I'll just go on to an example of this kind of dynamic programming applied to this Fibonacci sequence example that we looked at previously. So this is a kind of slightly modified example of the Python code that I gave you before. So which illustrates this so-called memorized approach to dynamic programming. So it kind of highlights how so once repeated subproblems are computed, how they can be cached and then reused at previous subsequent steps in the execution of an algorithm. So so essentially this is what this code does. This is the same Fibonacci sequence problem that we looked at earlier, where you so you have the initial values in the Fibonacci sequence, f0 is 0, f1 is 1, and then what you do is, according to some kind of recursive relation, want to generate Fibonacci numbers up to some particular value n. Okay, so this is what we're doing again, but now we have this kind of additional kind of cache that we use to optimize the procedure. And so here this cache is well, it's used as an input to this function. So we have a initial key, it represents a keyword argument. It starts as none. So if we don't use any cache, then basically it's just set to 0. And then what we can do is so this cache is essentially a dictionary object. And okay, let me just read this, sorry. Okay, so again, apologies for this, but I won't go over all the details of this now, but this code will be put onto the Slack channel. So if you want to kind of understand this in a little bit more detail, then I encourage you to kind of take the code from there and to implement it yourself to see how this kind of cache works in comparison to the previous exercise that we looked at earlier. Okay. Oh, sorry. Let me just go back. Yeah. Okay. So I think let me just check to see how far we have until merge source. Okay, so I think maybe this is a little bit early, but I think it might be good now. So essentially what we've done is just finish this dynamic programming part. So I think maybe what would be good now is if it's okay that we can finish slightly early, and then when we come back, we can look over some explicit exercises for you to do yourself that involves each of these types of algorithmic designs that I mentioned. So this dynamic programming, the divide and conquer, and the greedy algorithms strategies. So if that's okay, then we can maybe break now, and then we will reconvene. I think I'm not sure how long lunch is, so maybe somebody can clarify what time we reconvene.
That's 1:30, Graham.
1:30. Okay, thanks. Yes. So we'll come back with some examples or some exercises as well for you to do after lunch. Okay. Hi, everyone. Sorry for the delay on our side. I think we can now reconvene for this afternoon. So if I'm correct, this afternoon we have a number of worked through examples that Deepika will outline for you. So yeah, I think I can hand over to Deepika if there's anything else to mention. Thanks.
Thank you, Graham. So this afternoon, like Graham said, we're going to do some of the exercises. And what I want to start with is expanding on binary search. So earlier on, Graham introduced binary search in pseudocode. So I hope everyone understands the logic behind it. And I just want to do this code along in Python, because that's the language you've been working in this week. So I'm using VS Code, but you can use whichever editor you're using. And we're going to create a new file, which we want to call binary or binary search .py. And I want to give some background onto binary search. So as we all might know, binary is a term that refers to two parts or having two choices, yes and no, true or false. Binary is used to, this binary algorithm splits a sorted list into two halves. And I say sorted list because this is a key part of making sure this algorithm works. The list has to be sorted in increasing order from smallest to largest. So keeping that in mind, we're going to make the function called, this is how we call a function. And we'll name it binary search. I hope I'm not going too fast for everyone. So this is how we define our function, binary search. And I put inside two variables, ARR for array and targets, which is what we are searching for. So when we search for something in binary, we usually start from left to right, simply because we are splitting. So we're going to create two variables named left, which is, of course, the smallest, and then right, which is the largest. So this format, I'm just declaring two variables at the same time, and a comma splits them. So left starts at position 0, which is the beginning, and right is at the end of our list, which is indicated by the length of the array that calculates how many elements are in our array. And the reason we say -1 is because in coding, in computer science, the way lists are numbered is not 1, 2, 3, it's 0, 1, 2, 3. And so just because of that terms, if we have 10 terms in our list, it will be actually term 9 in terms of computer science. So that's simply why we put length -1. Now, of course, to do this search, it's very repetitive to have to keep on halving this list until we find the target or the value that we're looking for. And to do that, we use a loop, or more specifically, a while loop. So we will start by declaring our while loop. And as I referred to the logic behind it, we're always going to run this loop while the left side or the first term is smaller than or equal to the right term. So what this condition does says, while the first term or the smaller term, which is supposed to be, is smaller than equal to the bigger term, then our conditions will be carried through. And then we also want to declare the mid of the list. And how would we do that? We would take the left and then we'd add it to the right. So in this case, left is 0 and we say right is equal to 10. So 0 plus 10 is equal to 10. And that's the length of our list. And then to find the middle, we will divide it by 2. And what the double slash does is it ensures that the number will not have a remainder, it will be a whole number. So now we are thinking we have the middle, we have the beginning, and we have the end. Now we want to check. We want to follow the logic. So we're going to say the easiest statement, which is if our target or the number we're looking for is the middle, then just return the middle. So that's as easy as if array is the middle. So the square brackets means the position. And over here, we declare the position, which as our example would be 5, is equal to the target. Then we'll return mid or the middle. So that is our one if statement. Our second if statement would be else if or elif. Elif, the middle of the array is smaller than the target. Then we're going to say, we're going to redefine the left variable. And we're going to say mid plus 1. And what this does is it essentially discards the left half, because if our target isn't, so the middle of the array is either split into one half or the second half. If our target is not in the first half, we're just going to get rid of it. And then we're only going to look at the second half. And now we are going to split the second half into another 2 halves, or essentially quarters, and look for it there. And that's where our loop will rerun. So that is if it is not in the first half or the left half. So now we have to have the counter argument, which is the right half. Identical, but just the opposite. So then the right will be the middle minus 1. And this discards the right half if we find out that our seeked value is in the left half. And then because a while loop can go on forever, we need to have some termination that if our while loop is not true and the left half is actually bigger than the right half, we're just going to return -1. So this is the function that we've gone through. And I hope that I helped to understand it a little bit more, and that it's actually just a loop of halving and halving and halving until we find our way there. But I think a better way to see this visually is if we can apply this. So we're going to use it in an example. And all I'm doing is going to make so we can run this. So I think everyone is familiar with if name is equal to main, because then we're able to run an example. We're gonna oh, sorry, let me just zoom in. I hope that's better. Okay, so I hope everyone can see now. Let me just oh, I see now. Sorry, everybody. I did not see the messages on Slack, but I will check more often. So as I said before, binary search takes two arguments, which is two variables, which is array and target. So we're going to define our array. And this can actually be just a list of any random numbers. You can make it however large you'd like it to, or however small, but I think a decent sized list can show just how impressive binary search is. So as I'm writing this array, I hope everybody keeps in mind that yes, binary search is very impressive. It's very effective in the fact that it's a logarithmic function. As you might have heard earlier, O log n function, which is a logarithmic function, and it's very time efficient. However, it does need to have the array sorted beforehand in ascending order, which is a little bit of a hassle, but I think everyone will be familiar or understands that you can write a small code of 2 lines or use a built-in function in Python that says sort and then your array. And then you can just take the return of that and plug it into this binary function. So now I will define our target. Which is, let's say, we don't want it to be too easy that it's the middle term. So we will make it 101. And now just to display these results, we're going to create another variable named result. We're going to call our function binary search and then ARR as we defined above. So the computer will take these values and target. And then we're going to put a condition just in case of any extreme possibilities. We're going to say if result is not equal to -1, then we're going to print element found at index and then print our result. I hope everyone is on track. I see a comment, why do we write the name with underscores? It's just the syntax that is used in Python, simply because possibly if name was a variable, it doesn't get mixed up with this name. Can I paste the previous part of the code? Of course. I pasted the function into the chat. Now to continue with actually displaying this, so we can see that our function has worked, is an else statement, because I only want to have two conditions. Else we will print element not found in the array. So this portion of the code could have been done numerous ways. We could have said if result equal to -1, then we could have put element not found, and then we could have just printed the result. We don't even need this code if you just want to see the result. The only reason we put this condition here is because we ended our loop by saying return -1 if there was no value found. So I hope everyone gets a chance to run this code just once off and see if it is functional. So I'm going to run my code. Element found at index 6. That is my output. And let's just check 101. So we're going to check. This is position 0, 1, 2, 3, 4, 5, 6. That's correct. Thankfully. What is the purpose of line 18? This is just it's formalities for Python code so that we can run a main script. This is what allows us to run our function. For example, I can take it out if you'd like. And can show you another way to do it. So similar to what I did, this is a shorter method. I'm just printing the result of my function. As you can see, it looks a little bit messy. And that's the only reason that we use if name equals main. It's just formalities, and it allows somebody to easily and quickly look at the code and change certain parameters like array and target to get their wanted result. If array equals and then we'll define our result or our target. And then we can run it again. See, it will just give us the output as 6 because I just got the result. And instead of having the statement element found at index. I could argue your if name equals main is not, it's not necessary, but once you start coding larger projects where you have to handle a lot of algorithms at the same time, it's very handy just to keep everything in one place. Yes, the code will only work if the list is in ascending order. An error saying name doesn't exist, please can you make sure your syntax is right? So it's underscore underscore name underscore underscore space is equal to in quotations underscore underscore main. So these two lines are actually a double underscore. Name. Okay. Well, as I said before, if name is equal to main is just a syntax. It's a way things are done. In that case, it is just fine to copy it. And you will understand it further along in this course. But now I'd like for everyone to play around with this code, and we can find ways to almost make the most of every condition that we've coded. For example, I'm going to change my target and choose the number 5 simply because it's not there, and I want to do this because I want to see if there is a hole in my code. And this is known as debugging. And there we go. Our condition works. Element not found in the array. I can also show you why this list has to be in ascending order. One, three. Simply because this code works on the comparisons less than equal to, more than equal to. And because the computer is assuming this half, all of the values in this half will be smaller than the value in the other half, that is why it just discards it. It doesn't actually go and check every single value. And that's part of why it's so fast, but it's also a fault. Okay. I hope everyone is up to speed. So what I'd like everyone to do is just play around with this code, maybe test its limits, test its space. I know a very interesting thing you can do is make an incredibly large array in ascending order, of course, and just test the speed output. Why? Because this binary search has a logarithmic time complexity of O log n. And n is the number of elements in the array. And because this search space is halved every time, that is what leads it to the logarithmic number sets, as I said earlier. And that's what increases the speed. That's why it's so much more efficient than a linear search. And it's very effective using large data sets. And it's straightforward to use as long as your array is sorted. On an interesting note, binary, if anyone is interested in more different types of way information is listed, for example, not an array, but in a linked list. So people might be interested in linked lists because of upcoming AI. And the theory in basic terms is linked lists has something to do with how AI works. So binary is, of course, not as efficient as linked lists because accessing the middle element takes time. Could I please paste the current code? Here is the current code. I think this is a very lovely question. If left is 0, then right will always be greater than it. So how does the while loop stop? Well, the while loop stops if it satisfies one of these conditions, which is when the middle is equal to the target. So essentially, we are shrinking our data set until we meet the middle. And the middle will be our target. So it just keeps on shrinking until we find that number that we are looking for. And that is what ends our while loop and doesn't make it continue forever. Okay. It only outputs one index. Okay. So there's another very interesting question. If a number appears or is inputted twice or more in the array, how would we deal with this in terms of processing? Well, I think that is a very interesting thing that should be a challenge. And we should, I'll give maybe, it's 10 past now. I'll give 15 minutes and someone needs to find a condition somewhere that we can put in if there are this many repetitions of this number, we count it as 1. Or we remove it from the list. So I hope everybody can understand the hint I'm giving, that if a number appears in an array more than once, we can either check that array beforehand and eliminate the repetitions, or we can check it in our loop. So I hope everyone tries that, and in 15 minutes we'll rejoin and look at the answer. Okay, it has been 15 minutes. It is now 25 past. I've been looking at the Slack chat and everybody's code that they've been willing to upload. So I can see an attempt by Joshua, an attempt by Louise, and Awad Al Karim. And these are all, this is what I love about coding. It's looking at everybody's attempts and seeing how everybody approached it from a different angles and still got the same output or the achieved output that we wanted. So now, during this 15 minutes I gave, I also attempted it myself. And I don't know if anyone else approached it the way I did, but let's go through it. So what I did first is I actually changed my function to binary search with duplicates, simply because I just didn't want to mix up my functions. And it starts off the same with the left and right, which is my beginning and end. And I actually put first occurrence is equal to -1. So why I did this? Just so that I could show a difference between the previous code and this code. I did see some comments in the chat about why use -1. That is a very valid point. I actually did not have to use -1. It's just a term that is very commonly used when something is proven not to be true in a while loop or you want it as an exit. I could have also said return cat or dog. I could have said return exit even, but preferably don't use exit because it is actually a function as well that will cancel your code exit. So if looking at -1 is a bit daunting to some people, you can just rename it. You can say first occurrences equal to -1 or return some sort of variable that we can make it correspond with what we're going to use in results. So if name is equal to main, again, I know that was very confusing and I apologize because I know not everyone is from a coding background or it is quite abstract to think about. So that is why it's just the best to copy it. So now I've put repeating values in my array. I put 3 5s and I said the target is 5. So what I do now is I said results is equal to binary search with duplicates, array and target. And then I put the same conditions. If result is not equal to -1, print for function. I like to use function, but you can add strings or concatenate them with the plus symbol. I just find function is easier because you can just quotations and then insert your variables using curly brackets instead of having to go element quotations and then plus and then quotations again and then say string version of target. It's just, but by all means feel free to. I'm a lazy coder. And then basically what I did is I actually just repeated the code for however many occurrences. So as you can see, that was the first occurrence, which is why it was identical to before. And then this is the second occurrence. and then the last occurrence. Now, if I run this, you can see it says found at index 2, found at index 2, element 10, not found in the array. And that's just how our conditions have been working. But if I look at a different approach where maybe you don't want to look at the different occurrences and you just eliminate it, I like the approach of sorted and set array. Yeah. So I hope everybody's following along and had some fun playing around with this code. Let me save it. Will this still work if the target isn't the same as the repeated number? I hope I'm pronouncing your name right. Javiera. I think I don't really understand what you're asking. If you mean the target isn't the same as the repeated number, so 5 and 555, it would still work because even though the number is repeated, it has its individual place in the array. So even though it's 5, the index would be counted as, for example, in this array, it'll be position 2, position 3, and that won't affect anything because even when we split the list, if you look left and right, 5 will be, sorry, 5 will still be, let's say, smaller than 7, or it will be larger than 3 in all cases. So if we looked at this array and our target number was not 5, but it was in fact 29, then what the code will do is it will run and it will find the midpoint. There's 8 positions, so the midpoint would be 4, in between 4 and 5, which is 5 and 5, and then it would split and then keep on splitting until we actually reach 7. I'm looking at Sarah from UP. I like this code because it actually deletes the duplicates, which I think it's still fair. Yes. Oh, and I get a response from Javiera. What I mean is 5 is repeated, but our target is something like 101. Yeah, it really won't affect your code just because the number 5 is repeated. Even if your target is 101, it'll just iterate over it and you will achieve the same value. Okay, so I like the creativity I'm seeing in the chat with everybody's code. I'm looking at Zoe's code. Zoe, that is completely correct. Thank you. I'm looking at Kyle's now from UCT. Okay, so Kyle actually used an indices.append function, which I think is lovely, and the dot sort function, which I referred to earlier. I'm glad you use that because it just gives you that ability to put in any array, not having to worry that it's sorted beforehand. You just click the run button and it is in ascending order. Can we use binary search on array list or linked list? Katleko, I'm glad you asked this question. Binary search cannot be used on a linked list. It can be used on an array list. That is what we're currently running it on. If you look at the code here, the square brackets is actually an array list. If what you mean by an array is, can you use a binary search on a 2D array? That means it has both an X and a Y axis. It's a grid almost. Then the answer is still yes, but in taking into account that we would take that 2D array and actually make it into subsets of an array. For example, here is our array, and then we have another array within that array. So that is actually a 2D array. This is a 2D array because it has an array within an array. It's quite funky. Can I please paste my code? Yes, I will. I apologize. I should have pasted that a little bit earlier. I have now pasted my code in the chat. So going back to Katleko's question on array list and linked list and whether we can use binary search on them. I'm glad you brought that up because after the break from 3 o'clock to 3:15, we will briefly look at a different type of search that can actually be used on a linked list and not an array, or even it can be used on a graph. So while everybody is looking at this, and I hope everybody understands the ideology behind this code and how it reiterates in making something a smaller and smaller data set to sift through. Now, looking at the chat, I see everybody seems to be comfortable. Those people who posted their code, I'm very happy. And now that I see that this challenge I gave you, it doesn't seem like much of a challenge for you guys. So I want to up the bar in these last few minutes. How many minutes do we have? It is almost 1:45. So in these last few minutes, because we've been dealing with numbers so far, I want everyone to just try their very best. Even if you can't, I don't mind, as long as you give it a try at the end of the day. Instead of using numbers, a number array, how about we use a bunch of letters? For example, A, D, Z, and yeah. And using these letters, the same concept, except, for example, we're going to have B is smaller than A. So you have to sort your array into alphabetical order. And then I want everybody to use the same concept of binary search, but we're going to look for a letter. So say I have the array, let's make an array. Let me just, so that we can work on it. We're going to say this array is equal to, because we're using alphabetical letters, it's not going to be a number, it's going to be in quotations because it's a string, which is also what makes this challenge a little bit more complex. We're going to start simple, A, B, D, P. Let's say, now let's throw E in the mix. Let's throw E in the mix because E is supposed to be here. And then Z, X. So let's see if I'm being fair. 0, 1, 2. And Y. Just so our list is an odd number of components. Now I hope everybody can write me a code using the method of binary search so that we can first sort this array of letters into alphabetical order. And then from that, we are going to find our target, which I want it to be, I'm going to choose, yeah, I'm going to choose Z, but everyone can feel free to choose their own letter. Of course, please don't make it easy and choose the middle value. And we will meet just in 10 minutes, if that's okay with everyone. And then in 5 minutes, we can just see where everybody is, and then we'll go on break. If everyone wants to still keep on working on it during break, feel free to, and then we will see how progress has shown. So I'll see everybody in 10 minutes, and then we'll just regroup, and maybe I'll give some hints if it was a little bit too difficult for everyone. So I've looked in the chat and I see I'm very happy a lot of people have attempted this, and I'm extremely happy that nobody fell for my little trick here. I'm glad people realize that you can treat a number and a string very similarly in this situation of binary search, simply because we are equating them to each other and there are no conversions involved. How can we return to the original index and not the sorted index? That is a very valid question. And the way we do that is we actually have a separate array that we store the positions in for specific values. So we'd make a variable of the original index called original underscore index. And then we'd sort the index, and then we'd find that position. And then instead of, we'd have the position, and then we'd uncover what number is in that position, and then research. So we'll just say find value in original index, the original array, and then it'll give you another index, which is your final answer. I know that was a little bit all over the place, but condensing that is you'd save the original index. Of course, you'd sort it and then make another array called your sorted array. From that sorted array, you find your value. From that value, you understand what value it is, and you can actually discard the information of where it is placed. And then you cross-reference with the original index where of that value, and then find out what the position is. And I hope that answered your question, Drew, from UP. Yeah, so I'm very happy with everybody's responses. I'm glad that everybody has an understanding of Python, how the letter and the number can be interchangeable in this example, and you really had to change the argument. You really just had to change the array like I've given, and the target, so that there are no numbers involved. And looking at everybody's codes, I see some of you have taken it that further step of now finding repeated letters, and that's very impressive. Same concept again. And I see Sarah, who, no, I apologize. Someone, okay, well, someone in the chat did something that I think is a very practical approach, and it's actually how people work with data in the real world, and it's you given a value of numbers, and these numbers aren't necessarily split into the form that I have asked, or the computer processes it, which is in the form of an array, and the letters are split up in all quotations, such as C, or it's split up by a comma, 1, another quotation, X. What I'm trying to get at is you can actually use a function called split. So I got, for example, I get this huge data set of numbers from a previous lecture I'm quoting on Friday. It was coordinates, and you want to split these coordinates. You can use a function split, and it will split up these numbers, and then the computer can then run this code without you having to manually input 1 quotation, close quotation, comma, 2. It's an automated process if you use the function split, who I'm trying to find here. Yeah, well, whoever did that, thank you. That's another very interesting point for someone to look at. So on that note, I hope everybody had fun with this binary search topic. And now we will actually go on break for 15 minutes, and then we will discuss another search algorithm that is not restricted to just a linear array. So I'll see everybody after the break. Thank you. Welcome back, everyone. I hope you had a nice short break, stretch your legs, or had some nice time to just play around with this code. Now, I would like to start and end of our day with this last program that we will go through, which is another search algorithm. So if everyone would like to create a new Python file, we'll call it bfs.py, and we will start this next part of the section in a new document. Just gonna wait for everyone. If someone can like give me a thumbs up when we can commence. Okay. So first, I want to give some background on what BFS is. Maybe some of you know, maybe it's some of you don't. So BFS is an acronym for breadth first search. And it's quite a mouthful. So that's why we often say BFS. And it's a crucial algorithm for traversing or searching graph data. So in chemistry, you get compounds, and for example, the hydrogen molecule, which is H2O, which is O with a branch of a H and another branch of an H. And even in probability and statistics, you get graphs of actually interaction between letters. I think a better way, because I don't know for everyone here, but I'm a visual learner. And so I'd like to show you an example of what graph I'm referring to. So let me just make a text file. And start. So here is a simple graph I want to show. And it's a linked so it's almost like a tree diagram. It's everything's linked between connections, joins, nodes. As somebody mentioned previously before the break, linked list. This is what a linked list would be represented as visually, of course. And F. So here we see, let me zoom in. Here we see a graph of letters A, B, C, D, E, F. And, oh, okay, let me zoom a little bit more. The letters A, B, C, D, E, F. Let's think of this as a graph, and these letters are different locations. So now, if we wanted to find our way to F, we can either take the route A, B, E, F. We can take ACF, which is the shortest route. We can take a scenic route of A, B, D, go back to B, go A, C, and then F. You can see there's many various ways to actually get to this different position. Now, what breadth first search does is it looks at a set of data, which is actually represented like this. So let's say this is position A. It has a connection with B and C. And then we look at position B, which has a connection with D, E, and A. So this is how the data is represented in a computer program. And these are basically the values we're going to give into our algorithm, and it's going to do a search, and it's going to actually calculate which path is the shortest for us. So this new function that we're going to make in our code is going to be called BFS, for breadth first search, shortest path. Okay, I hope everybody is following along. And if you don't understand, it's okay, because I think we will learn along the way. It's intuitive. So looking at our graph, we of course have the answer already. Well, we have the graph, and I think the answer is very visible. You can easily see it because it is a very small graph over very few elements. Of course, if we expand this on a larger level, it's going to be much more difficult to just eye the answer offhand. And this is why this algorithm is so important. So of course, we need to think. Computational thinking is something that's almost natural to us. So if we had to think how we're going to write this algorithm, we would think, well, of course, if I look at this picture and I think, how do I get the shortest path? I want to start at A. And that's just it. We're going to need a start. Well, first we're going to need a graph, of course. So we have this graph, which is one of our variables. And then we have a start. But then, as well as a start, we have a goal. We want to go to F. So we're going to create another variable, goal. I hope everyone's following along. Thank you, Carlene from SU. She's given some background on it, which will be available in the notes that we release later as well. Yes. And this is very accurate and interesting. Thank you. Another concept that we have to explore when looking at breadth first search is queues. Now, queues is obviously like a waiting queue. It's also a concept in computer science of how we handle data, how we handle information. And a queue, when you use a queue, it basically means first in is the first out, compared to its counterpart, which is a stack, where the first in is the last out, simply because it's a stack. If you put it in first, it's obviously going to have to come out last. And if you stand in a queue, the goal is if you're there first, you're going to be served first, in our case, in a hopeful world. So we're going to use an import. We're going to say this import comes with the Python package. So hopefully everyone has this package and won't have issues downloading it or accessing it. We're going to say from collections, import DQ. And we will see how this comes into play later. So if you think of the terminology queue, which means you're standing in line, or you've joined a line or a system, then DQ simply means you are leaving this line. So I just want to see if anyone has issues with this import. I'm hoping not. Can anyone confirm? No issues. Thank you. Okay, let's get started. So now we have these parameters in our function, our graph, our start, our goal. And like our previous search function, this function is going to be iterative. It's going to be looping. So we're going to use a while loop. But of course, before we use a while loop, we're going to have to set some of our variables that are going to be involved in our while loop. So I want to create a variable called Q, QUE, UE, is equal to DQ and your start variable. And then visited. Because of course we have to, the computer is not going to know offhand which path is already the optimal path. It's going to test all the different paths, and we're going to obviously have to keep track which ones have been visited to know which one is the shortest path. And we're going to set our variable visited is equal to set brackets start. Okay. So now that we have these variables declared, I just wanted to point out, yes, I was just going to mention, Natasha, why we have so many square brackets. I think the best way is to show you. So why we have so many square brackets is because we are dealing with, this graph is of course 2D, and there's no way to take this graph unless we use ChatGPT, of course, or DeepSeek, to take this graph as a photo and just input it into our code and say, give me the shortest path. We have to put it in this format of a list. And because it's in these square brackets, it's in this list, we are simply accessing an array. So in the array, we are accessing start. I hope that answers your question. Now we're starting our while loop. So Q is our variable that we declared. So while Q, which is also another way of saying while Q is true, or while there is a Q, then this will recurse, or this will loop. So while Q, we're going to declare variable path is equal to Q dot. So we are accessing a function from this Q import, or from our Q variable, pop left. So I just want to define node, and then I'm going to explain what the pop left means. Okay. So what pop left is, it's, as you can see, my computer's already highlighted it. It's a method that we accessed from this collections import DQ. And what pop left does is, I'm going to use the queue example. So we're standing in a queue. What pop does is it, in this context, removes someone from the queue. And there's another function called push, which is what puts someone in the queue. So what pop left does is it removes from the left. And node is another way to think of this graph as different nodes. So that's why we're naming it node. And then path -1 is to get the last. So -1 in square brackets indicates its location or index, and -1 index means the last. Now we are going to implement a statement if node is equal to goal. So if the node that we are at, or the position we are at, is equal to the place that we want to be, of course, that's amazing, because that means we found our path. And we can return path. And that means we found it. Something I'm guilty of is we should be commenting a lot when we code. I hope you guys are commenting every line just to remember a point or two on that line, or show that you understand what's happening. It's very useful to comment on your code and then come back to it maybe months later and then still remember what you've done. So if our node is equal to our goal, we're going to return the path we found it. Well, that's the ideal case, of course. Now the not so ideal case. For neighbor, in graph. So of course we declared our graph here. In graph dot get is another function. Now this is our for loop. And I want to explain it because it's going to get very information dense from here on. For neighbor is a counter. I think many are familiar with for I in range. Neighbor is just replacing that I. And graph.get node is just the position, and is the position of where we're going to be iterating through in our for loop. And then the empty brackets is just, it's a placeholder. It's part of the array. So now we're putting an if statement in our for loop. So I hope that you know we're going to have an indent. So why I'm speaking of indents now is because a very common run error code is if you forget to indent your if statement in your for loop. So if I just carried on from here on, whatever, it's not going to read because we need to have our information inside of our if statement. For those who might not understand what I mean by neighbor, it's not just a random word. The reason I say neighbor is because if we look at this graph, we can say that A's neighbor is B and C. B's neighbor is D and E. C is neighbors with A and F. And that really just further makes sense of this notation where A has the neighbors B, C, B has the neighbors D, E, and A. So that's why we said if neighbor not visited. So if that value A, B, C, D, or E has not been visited, then we're going to say visited dot add neighbor. NE apologize, I spelled neighbor wrong. So what this does is it adds neighbor to this list of places visited. Let me just check the chat. Yes. Awadil Karim. He says, in programming, square brackets are often used to denote different things depending on the context. That is very true. I am making reference to nested square brackets, which is the double brackets we've used above. Yes, it is used to represent multi-dimensional arrays, which is what we're trying to represent this graph as. Thank you. And I think that is the best explanation. The outer brackets typically represent the main array, and the inner brackets represent the elementary of that array. Thank you. Can I explain what DQ does and why do path equals Q dot pop left? I see this has been answered by Colleen. Thank you. But just to say again, it's like if we're standing in a queue, I'm waiting for food. Pop means I'm leaving. It pops out that value. And then push means put into the queue. So pop left just means because this is an array, we're popping left. So we're deciding which direction we are losing from. Not or not in. It is not in. Thank you. And that was Avinash. So I hope we are all on the same page here. We got our double indent. And we can continue with our if statement. So now we said if our neighbor is not in visited, we must add them to our visited array. And we're going to create a new path. And we're going to say new path is equal to list path. So what this does is it redefines our path as a list. And I think I discussed this earlier. New path is basically we saving a path, in this case it's path, so that we can have multiple in our function. And we're going to say new path dot append, which I hope people are familiar with. Append means we're just adding to the list. So what we're doing is we're adding paths to a list so that we can keep track of all the different paths and then decide from there which one is the most optimal best path. And I'm going to say neighbor. And then finally, we're going to add this new path to our queue. Dot append. Once again, using append. And there we go. Between add and append, you can use add. I think append is more appropriate because we're going to have multiple paths in this list. I think what add does, it's more commonly used with single variables and not a list within a list. Okay. So now I have an open question for everyone. I just want to zoom out a little bit so we can see this whole function. I have an open question, taking into account what we learned in binary search. We talked about how the while loop is going to be infinite and we need to have some sort of stop if there is no path found. So if there is no shortest path or no suitable path, can somebody give me a line of code that we would input to stop this while queue loop? Q equals false. Very close, but not quite. That was very quick. Natasha from Bits. Wow, Bits. We are going to return none. That is correct. Because there is no path found. So we're going to comment there. No path. Thank you. Well, now we are done with our function. And we shall, oh, sorry, indent. We shall now test it out to see if this works. So we're going to once again, okay, now I know, okay, we're going to say def main. Oof, main. And just because this is a graph and it's not that easy to always just input for test sakes, we're going to store it in example graph is equal to, and curly brackets now, because it's going to be a lot of values. So I think we shall make this graph in this notation. For those who want to go ahead and because they can figure out the notation, please do. Otherwise, I will be slowly but surely typing it out over here. So B and C. And then node B connects to A. Oh, I apologize. We're supposed to be putting a comma after this. That's why the red line was appearing. Simply because of notation error. C joins to A and F. D, I remember D was a little bit sneaky. Yes. D connects to B. I do apologize. That graph looks like it's connecting to E as well, but it's just B. And then E connects to B as well as F. And F connects to C as well as E. Okay then. Adding on to that, we're going to declare our variables. I'm going to say start node can be A for alphabetical sake. Goal node F. So right now we're just declaring our information that will be used in this algorithm. So now we are at path. I hope everybody's with me. Let me just check. Do the alphabets have to be in order? Not necessarily, but I put it in order simply because it affects processing speed, and as we did, you guys did a little bit of realizing how to calculate how fast the computer processes, and what this does is it just makes the algorithm a bit faster by putting it in sequential or alphabetical order. So now we're at path equals BFS shortest path. We're going to input our variables, which is graph, start, and goal. So our graph is example graph. Our start is start node. And our end, well, goal is goal node. Once again, we have an if statement. In this case, we're just going to say if path, because we don't have a term to say if not equals to -1, because in this case, we didn't use -1, we used none. So we cannot say if not none, or this is another way of saying if not none. It just means there is a path. Then we're going to say print. We're going to print function shortest path from start node. I hope you guys don't mind I'm speeding up just so we don't have to end too late. To goal node. Path. So what this sentence basically says is shortest path from start to the end, and it's going to tell us which path to take. Else, because we need that other statement, print. No path found. No path found. Because in the only other situation where there is no path is if there is no path found, of course. And this controversial line, if name is equal to quotations underscore main, and what we're going to do is call our main method. This is our main method. I hope I didn't lose anyone. Feel free to run it if you can I explain how F is connected to C, not E only. C, not E. I don't think I understand your question. Paulina, F is connected to C and E. If I can demonstrate from this graph, F is connected to C, F is connected to E. I hope that helps. Oh, if everyone is with me, you can run your code. And it should give you the output. Yes. Oof. Let me zoom out. There we go. Shortest path is from A to C to F, which is what we concluded with when we first looked at this graph. From A to C to F. I hope this is very interesting to everyone, and I hope you feel the need to experiment with it further, make it more complicated, and make a huge web diagram of this and see if your code can handle it. We have a few minutes left till the end of the day. So no output, but it is running. Let me see. Run main. Is everybody having this no path found, my output? No output, but it's running. I think I have the same issue where it is running, but there's no output. I will paste the code in the chat. Let's check this. Yoni says remove the indent from main. Not too sure. But I hope you look at the code pasted in the chat and that it runs. The line above it. Oh, yes, yes. Thank you, everyone. That was a silly mistake. If name is equal to main, we indent from the beginning. I did not see the extra line. I had it. Thank you to everyone who showed me that. And yeah, it should run. On that note, I hope everyone had a good day today and enjoyed computational thinking, and that you all found it interesting. And I'd like to end off the day on that note. Thank you everyone for joining. Thank you for listening and coding along. It was great having you guys. Thank you and have a good afternoon.
Thank you, Deepa. Thank you, everyone, as well. Thanks for attending. Thank you.